last lecture, we discussed the particle moving in a one-dimensional box. So let us summarize it. Such a particle has state functions psi n, normalization constant times sine n pi over a times x, and the related energy levels are where n is 1, 2, 3, and so on. And the normalization constant is square root of 2 over a. Okay, so for example, the ground state wave function is for n equals 1. And the ground energy level is simply Fs. Let us also remember that Fs is h square over 8 times m a square. So, okay. All these functions are eigenfunctions of the Hamiltonian, and the Hamiltonian for this particle is just kinetic energy, and the kinetic energy is simply p square over 2m. They satisfy all these functions. More explicitly, p square over 2m psi n equals En psi n. All right. Let's have some examples. What is the average value of square of linear momentum? Momentum in the ground state. Now, average value means expectation value, and the general expression is average value of an observable A is given by general principle. Here, the observable is square of the magnitude of linear momentum. So average value p square is this is for state n. Now, we can do this integration. This is because there is just one variable in this problem, dx, and the integration is from 0 to a. This integration can be done by substituting this expression and then doing the integration explicitly. Or we may evaluate it more simply using this property here, because you see this part can be replaced by a simpler expression using this property. Two times m is just a constant. So just multiply this expression with 2 times m. 2 times m. Two is a constant, m is a constant, energy is a constant, En is this expression. All right? Therefore, when you substitute this expression here, but the value of this integral, what is it? 1, because we have selected a, the normalization constant, to make sure that the value of this integral is 1. All the wave functions are normalized. So this is, which means the average value we are trying to calculate is simply 2 times m times energy. For the ground state, the question is asking us for the ground state, so we just put n equals 1. So, average value square of the linear momentum is simply 2 times m times eps, because E1 is equal to eps. We can simplify it. There is a m here, so this is h square over 4 times a square. Please note that the units are consistent here. What is the unit for linear momentum? You can remember it from the classical expression mass times speed, kilogram meter per second. This is square of it. Therefore, in SI, the unit should be kilogram square times meter square times divided by second square. If you analyze the units of H, and A is of course length unit, you are going to obtain exactly the unit we are talking about. As another example, average position of the particle. What is it? What do you expect? What do you expect classically? This particle is in a stationary state and it's going back and forth. When it hits this wall, it travels backward, then hits that wall and then reverses the direction. So it's a motion like that. What do you think the average position of the particle will be in any state? Come on, just imagine the particle is moving back and forth, all right? And if you imagine what the average position of this particle is going to be, what would you predict? Exactly midpoint, isn't it? Because even though the states we are talking about are time-independent states, nevertheless, you may imagine for a very long time what should be the position of the particle if you average it. And common sense tells you that the average position of this particle should be exactly midpoint of the box. How do we calculate it according to quantum mechanics? Position of the particle is, what is the symbol, variable for the position of the particle? X. This is what we are trying to calculate. According to same expression here, the average value expression, we just put X here for the operator. But X is a multiplicative operator, so it just multiplies. So it is this expression. Now, let us substitute explicitly. You see, A is a real constant here. This part is also a real. Therefore, complex conjugate is the same as itself. And here we have square of A, and then x times sine square n pi over A x dx. So we do this integration. Of course, we need to use the integration by parts method to evaluate this integral here. But the net result, we will have 1 over 2 times A. And this is for all n. So whether it is the ground state or the first excited state or any state in this problem, the average position as calculated by this integral is 1 over 2a. But 1 over 2a, what does it mean? It's the midpoint of the particle. This is as a final example, what do we expect for the average linear momentum for this particle? Remember that momentum is a vector quantity. Think of it classically, all right? So part of the time, the particle is moving to the right. Then let us imagine if the particle is moving to the right, P has a plus sign. But once it hits this wall, it will reverse the direction. Then, by convention, P will have a minus sign. Is that clear? Going to the right, plus. Going to the left, minus. So if you imagine for a long time, half of the time the particle is moving to the right, and during the other half, it's moving to the left. What do you expect for the average value of such a momentum? 0. All right? Let us see if we get it using the same definition. Average value. This is the linear momentum of it. I have written here as a subscript x to make it more definite that it's related with the first derivative with respect to x. What is px? Minus I times h bar times the first derivative with respect to x. So let us simplify this part. Minus I times h bar, first derivative with respect to x, times a, times sine n pi over a times x. A is a constant, this value. These are also constants, so we have minus I times h bar times a. Derivative of this expression with respect to x is cosine times n pi over a. N pi over a times cosine n pi. So you substitute this expression for p psi in this expression, then you will get minus I times h bar times a times n times pi over a times the integral 0 to a which is sine n pi over a times x, which is this part. Sorry, there is also a square here. One of the factors a comes from the first term, and there is another a from the second term here, which is present here, times cosine n pi over a x dx. Okay, now suppose you did not know that the answer should be 0, all right? But what do we know? Average value of any observable must be a real number. It cannot be the complex number. It has to be real. This is just one example of an observable, the linear momentum, average value of a linear momentum. Therefore, this should be a real number. Now, if you examine the right side without doing the integration, all right? But what can you say about the value of this integral? Is it possible for this integral, the result of this integration, to produce a complex number? No, everything is here real number. This is a real number, isn't it? The result. A real number n pi a square here, h bar, everything is real, but what do you see? Complex number I. Then you ask yourself, this is the result of average value of any observable cannot be complex valued. Therefore, what is necessary to get rid of this I here? The value of this integral is necessarily must be, what is it? 0. In fact, if you do this integration and put the limits, you are going to obtain exactly 0. This is required because the average value of any observable cannot be complex valued. For any n, when you do this integral, in fact, this is a simple integral, isn't it? Sine times cosine. Its indefinite integral is sine square divided by 2. Upper limit is a. Lower limit is 0. In the lower limit, x 0, sine square 0 is 0, isn't it? In the upper limit, put a. This is sine square n pi. For any integer n, sine n pi is 0. So, doing the integral explicitly, we are going to obtain 0. But even if this, we did not explicitly do the integration, we could still conclude that the value of this integral is necessarily 0. Otherwise, the average value would have been complex valued, and it is not possible. Okay. So I think this is enough for the particle in a one-dimensional box. Now, let us go to another application. This time, we have a particle moving in a two-dimensional box. So the situation is like this. Now, the particle has 2 degrees of freedom, which means 2 variables are needed to locate its position. If this is the origin, we have a box, a wall, restricting the motion along the x direction. And so the situation is we have a two-dimensional box. There is a particle, all right? This particle has 2 degrees of freedom. It can move either along the x direction or along the y direction or in combination. Values of A and B are given to us. Mass of the particle is also given to us. The question is, what are the allowed energy levels of such a particle, and what are the corresponding state functions? Variables of the particle are x and y. X and y are independent variables, all right? Please note that by definition, probability of finding the particle outside of the box is 0. We know it, right? The particle is trapped. The particle is inside. It cannot be on this side or this side or this side or that side. It's trapped. Probability of finding the particle inside the box is 100%. In other words, probability of finding the particle outside of the box is, by definition of the problem, 0. All right? The particle is trapped. Now, what is the Hamiltonian? Hamiltonian is kinetic plus potential energy. In this problem, we are assuming there are no forces. If there is no force, the potential energy is a constant. And the value of the constant is arbitrary. And we choose the arbitrary constant to be 0, which means Hamiltonian is just kinetic energy here. Now, this is equal to p square over 2m. But now, momentum has how many components? 2 components. So that square of momentum is px square plus py square. All right. What is, now make it explicit. minus h bar square times second derivative with respect to x plus 1 over 2m minus h bar square times second derivative with respect to y. These are partial derivatives. X and y are independent variables. Now, what is our problem? Or what is the Schrödinger equation? Simply h psi equals e psi. Now, when you look at this explicit expression for the Hamiltonian, what do you see? There are two terms, first term, second term, and these are added. Okay? Remember, before we started the applications, we discussed the problem of independent particles, particles that are not interacting with each other. And we said if H has the form, for example, for n equals 2, all right, then for this problem, we have the energy, allowed values for the energy are E1 plus E2, and the wave function is a product, psi 1 times psi 2. Okay? Now, how do we recognize, how do we understand whether the particles are interacting or not interacting? The condition is this. The Hamiltonian should have a sum form, H1 plus H2, if there are more particles, plus H3 plus H4, etc. But what is important is each term in the addition must contain just independent variables which are not present in the other terms. That's the condition. And then we say the mathematical term is separable Hamiltonian. Physically, it means non-interacting particles. Now, we look at this expression. The first term contains which variable? X. Does it also contain the other variable? No. Look at the second term. The second term contains which variable? Y. Does it contain X also? No. Exactly the form we require. There are two terms added. Each one contains a different variable. So this is like, let us call this a one variable Hamiltonian in which the variable is X. This one, call it HY. Okay? Hx contains only X variable, Hy contains only Y variable, and they are added. Okay? Now come to here. This is a general expression. Number of variables in H1 and H2 doesn't have to be just one variable. It could be two variables or three variables. All right? But it's a general expression. What does it say? The total energy is the sum of contributions from each particle. And the total function, wave function, is a product. In this problem, in this example, we have just one physical particle. But by comparison of the mathematical expression with this general expression, we may simplify this problem mentally. How? We may imagine that by looking at this expression, of course, there are two fictitious particles. Fictitious, what does it mean? Remember it from fiction. Non-real. Two fictitious particles. There is an X particle and there is a Y particle. All right? Such that the X particle is moving only along the X-axis. And the Y particle is moving along the Y-axis. And these two motions are independent. So, the solution of this problem becomes very simple if you think this way. Why? Because then now you say the energy, the total energy of the system contains two fictitious particles. Remember that only one real particle. But mathematical structure fits that expression. The total energy, according to here, independent contribution from each particle. Let us call one of the particles energy of the X particle plus energy of the Y particle. All right? And the total function, total state function, is state function for the X particle, which is explicitly a function of the X variable, multiplied by a state function for the Y particle. Don't confuse the symbols, that symbol with that one. Here, this subscript we are using to label the particle, X particle, Y particle. The symbols inside the parentheses refer to the actual values of the variable. Remember, X variable ranges from 0 to A, and Y variable ranges from 0 to B. Okay. Now, which numbers are allowed for the energy of the X particle? We have just done it before this example. What is X particle doing? It's moving along one-dimensional box with box size A. So allowed values of X, Ex, are epsilon X times where epsilon X all right, I have erased it. Let me write it again. H squared over 8 times. Remember, mass of the X particle, fictitious X particle, and the fictitious Y particle are the same. So it's M. But here we have A squared. Similarly, allowed values for the Y particle energy are where this energy parameter for the y particle could be different from the energy parameter for the x particle. Why? Because the only difference is, instead of A, we have B. (8m) times B squared. All right. What about the related state functions for psi x and psi y? Psi x when you select an value for n sub x, you are selecting the energy of the x particle. The corresponding state function is this expression with the same value of the selected nx. For example, for what is the ground state of the x particle? The ground energy level is the lowest energy. Nx, you will select n sub x to be 1. Then the ground lowest energy for the x particle will be E sub x. What about for the lowest energy, ground energy of the y particle? You will select n sub y to be 1, and that is going to give you the lowest energy level. The corresponding function, state function, psi y, is similar to this expression. The only difference is the value of b could be different from a times sine n sub y times pi over b. And the y variable, don't forget the variable here, all right? Okay. So let us collect our results. The allowed values for the possible energies of this real physical particle are these are the allowed values. Now, let us also indicate which values are available for n sub x and n sub y. They are just integers, 1, 2, etc. And same is true for ny. Selection of nx value and ny value is independent. You may select any value for the n sub x and any other value for n sub y, including the same value. It is convenient to attach to the total energy subscripts which tell us which selection for nx and ny have been made. We do it this way: n sub x here, n sub y, two subscripts to the symbol for E. Okay, now let's ask, using this information, but before that, let me also write the total function, psi, This will also need two subscripts, nx, ny. Explicitly, this is 2 over a. These are normalization factors. These are our general results. Now, let us make it more concrete. What is the ground state energy for such a particle? What is the definition of ground energy level? Lowest possible energy, isn't it? To get the lowest energy, you need the lowest energy for the X particle and lowest energy for the Y particle. Two lowest numbers when added gives the lowest possible value for the sum, isn't it? Now, to get the lowest value for the X particle, what shall I select for the n sub x quantum number? 1. That's the lowest. These are positive numbers. Nx squared is also positive. Therefore, I have to select the lowest positive number. Similarly, for ny, what must I select? Also 1. So I can write 1, 1 means nx is selected as 1, ny is also selected as 1. This is the lowest. What is it? This is the ground energy level. Let us remember the concept of zero-point energy. What was the definition? It is the difference between lowest energy quantum mechanically predicted minus lowest energy classically predicted. Classical value for the lowest possible energy is 0 here. Why? Because it's kinetic energy, purely kinetic energy. Lowest value for kinetic energy classically is 0. This is the quantum mechanical lowest energy. Is this 0? No. Therefore, the difference between quantum minus classical is a non-zero value, and by definition, this difference is called zero-point energy. So, zero-point energy for this particle moving in two-dimensional box is just this value. Remember, this is a translational type. Making the box two-dimensional doesn't make the particle do some other type of motion, such as rotation or vibration. It is still motion along a straight line. So classically, such a particle, say at a given moment, if it is moving this way, it will hit the wall here and then be reflected. Maybe that way, and then, so it's that kind of motion, as you expect classically, all right? But these are the quantum results for the motion of such a particle. What is let us also consider the first excited state. By definition, all energy levels that are different from the ground level. There is only one ground energy level. All the rest are excited. The excited levels are numbered, starting with the lowest excited energy level. So to get the first, I have omitted the term energy here just to keep it simple in writing. When I say excited levels, I mean excited energy levels. All right? This is just short. Now, in general, this parameter x could be different from xy because A could be different from B. To get the first excited state, I may select 1 for nx and some number different from nx. So if I select this is one candidate for the first excited level, isn't it? Then I will write nx is 1, ny is 2. Now, another candidate for the first excited state is if I select these numbers in the reverse manner. So if I select nx is 2 and ny as 1, then my notation according to this, notice first index is nx and the next one is ny. So I write first 2, this one, and then 1. 2, 1. This is 1, 2. This is 2, 1. If A is different from B, do you expect this number to be same or different than that number? You see the expression. Note, okay, you forgot h square over 8 times ma square. If A is different from B, could this number be the same as that number? No way. Therefore, if A is different from B, this number cannot be same as that number. They are different values. Okay? All right. But our time is up, so let us stop here and continue after the break.